Hello, got a little bit of an extra special video for you just to give you a few more images. Section 1013 of your text does a great job explaining in detail about the different engineered lumbers, but there's not a lot of great pictures, so I wanted to add just a little bit of detail to that. One of the most common forms of engineered wood that most people are used to seeing out of chapter 1013 here is just plywood, where plywood are just thin sheets of ply that are glued up together. But what's really important is that you do at each layer turn the grains 90 degrees so that you get the same properties no matter how you cut that board and put it up. It has the same strength from either direction. To get the veneer that we make these out of, they actually soak logs and then they spin them on a giant lathe with a knife that just peels the layers off. Hopefully you've watched the quick videos on how different engineered lumbers are made and saw this process. But I do want to point out that it's not just plywood that comes out of this veneer. There's also laminated veneer lumber, and that lumber would be shaped either into plywood, but it also can be shaped into beams and is definitely often used as beams or the top and bottom flanges in I-joists that we're going to get to. Now, the additional boards that you might have out there is particle boards and chip boards. These are not structural members. Particle boards might be used to make that cheap furniture that has the plastic laminate over that maybe you have in your cabinet or your dorm room. And that's got no structural property to it. Chipboards sometimes get used for the more inexpensive cabinets you might find in a home store. The problem with chipboard is when it gets wet, it expands, not very useful. But the way chipboard's made is it is just using wood chips glued together, but it's all randomly oriented. There's no structure to how the chips are laid down. Versus oriented strand board. In oriented strand board, the strands are oriented in a specific direction to make sure we're getting strength in that direction, and there's a whole lot of glue that's used and a lot of pressure to create these boards. In addition to making plywood using this oriented strand method, you also make beams called parallams where the wood chips and strands are oriented down the longitudinal axis of the board, and you can actually make very strong beams out of this. One of the things you have to be very careful with oriented strand board is it's less expensive than plywood, so you will see a lot of contractors using it, but this is not good when it gets wet. So if you've put it up on your roof and you haven't finished your roof off yet and a rainstorm comes, or you get a roof leak later on, you can get problems with the structural integrity as that glue gets wet and you can damage the board. All right, we mentioned earlier that you can use that laminated lumber in your I-joist. Well, here is an I-joist. And so you have these top and bottom flanges. Now, originally, those were made from 2x4s or 2x6s that were notched, and then you actually put plywood in the middle as the web. Newer technology or just newer methods, typically you might have the LVL material instead, that laminated veneer lumber, as your top and bottom flange, and then your webs today are typically out of the oriented strand board. And these are I-joists used typically sometimes for your roof beams, but definitely for second story or first story over a basement floor beams because they're very strong for a much smaller amount of wood. But you have to be very careful where you cut them, and so you'll get directions on where you can put holes in them if you need to run electrical or plumbing horizontally through the ceiling or the floor below. And then the final, most common engineered lumber that's been around for a very long time, which is our glue laminated timbers or glue lam beams. And this is literally taking a 2x4 or a 2x6 and just gluing them up to make something bigger. I'd be surprised if everyone hasn't seen one of these somewhere. They're beautiful, and that's one of the advantages for them because you can make very large members that look relatively natural and allow for really special architectural designs, but you're not using big trees to do it. And the nice thing is you can actually use your cheaper wood in lower stressed areas. So if we look at this image from your textbook, just to explain why this is so important. So these 2x labeled 3 here, they're going to be your least strong wood. Even though that is where your shear stress is highest, in a very long spanning beam, which you would use a glue lam for, you're not going to have very high shear stress controlling it. It's going to be bending or deformation. So as we move out to the outer fibers of bending, where your bending stress is going to be maximum at the top and bottom, you can start putting your stronger members. And so, in fact, it's interesting. We can see nice tight grained wood. There's a lot of heartwood here. Up here, I have very open, fast growing wood. So I would say this is probably an unbalanced beam. And what that means is, obviously, if a beam is in regular bending, positive moment, it's smiling, I've got tension on the bottom. So I want a nice strong member where I have my tension, and so we can see the bottom two layers are really nice strong members. On the balanced glue lamp, so are the top two. Now maybe you're going to have reversed curvature and you'll have the beam go from smiling to frowning, and you need tension on both sides. Typically you don't in a regular building, it's just smiling. And so some people might say you could use less quality lumber on the top, like in the unbalanced glue lamp, and still be okay because that's a compression member. But one of the things you have to be aware of is generally a contractor or the laborer who's hanging your beams haven't had strength of materials and don't know about tension sides of members and understand the strength between the timber in tension and compression, and very easily, even though the beam is marked, this side up, could easily flip that beam around. So you might be thinking you're saving cost to the owner by speccing the less expensive beam, but then you, as the engineer, responsible engineer in charge, you are morally obligated to be out on that job site, not even morally, ethically and by code or by your licensure. You have to be out on that job site to make sure that gets hung up, or go out and inspect, and if it's wrong, make them do it again. And so you've just added additional cost to pay for your time that really the cost of the glue lamp and making sure it doesn't matter which way they hang it is justified. So this was just some fun little tidbits about the different kind of defects that are in wood or glue lamps. Here's some beautiful glue lamps actually in service on both this bridge and this church. Thanks for watching.